If I have a complex number, something like 1 on I, just like with surds where you have to rationalise the denominator, here we have to realise the denominator. So if I multiply the bottom and the top by the complex conjugate, so in this case minus I over minus I, that will realise the denominator and turn it into a real number. So the top becomes minus I, and I times minus I is 1, so that becomes minus I. So I and minus I are reciprocals of one another. If we have a look at another one, if I have 3 plus 4i, and I'm wanting the reciprocal of 3 plus 4i, I'll have 1 over 3 plus 4i, multiplying by the complex conjugate, so 3 minus 4i over 3 minus 4i. The top is 3 minus 4i. With the bottom, if you expand that trinomial, we end up with 9 plus 16. So our answer is 3 minus 4i over 25. An interesting pattern we have here, if we have I to the 0, that is 1. I to the 1 is I. But remembering that multiplying by I rotates around 0. And if we have I squared, it is minus 1. And then coming around the axis, so we start at 1, we go to I, to minus 1, then down here to minus I, then we come back around for I to the 4th, we're back at 1, I to the 5th, we're back at I, and so on. So we could keep going around, going from 1, I, minus 1, minus I, 1, I, minus 1, minus I, and so on. So because it's in groups of 4, then I to the 2015 would happen to be minus I. But notice that we're going anti-clockwise. But if I have I to the power of minus 1, it actually goes the other direction. So I to the power of minus 1 would be minus I. I to the minus 2, minus 1, I to the minus 3, I, and so on, because we are going clockwise this time. We usually denote a complex number with the letter Z. And if we let Z equal x plus iy, x here is the real part and y is the imaginary part. If x is 0, then z would just equal iy, so it's purely imaginary. If y equals 0, then z would equal x, which is just real. So if I've got z1 is 3 plus 2i and z2 is 1 minus I, if I want to just find out what the real part of z1 plus z2 is, if I add those two together, so 3 plus 1 is 4, and then plus 2i minus I is plus I, the real part is just the first value. So the real part of z1 plus z2 is 4. If I wanted the imaginary part of z1 plus z2, then my answer would be plus 1. Since the coefficient of I is 1, then the imaginary part is just 1. If z is in the set of complex numbers, and we know that the real part of z is 2, and we know that z squared is imaginary, then if we let z equal x plus iy, then we know that the x has to be 2 because that's the real part, so z equals 2 plus iy. But we want to have a look at z squared. So if I square z, I end up with 4 plus 4yi minus y squared. But since z squared is imaginary, then we know that the 4 and the y squared together, so 4 minus y squared, it has to equal 0. Solving that simple equation, we get y equals plus or minus 2. So therefore, z will equal 2 plus 2i or 2 minus 2i. If I want to solve this equation, similar to what I did in lesson 1, using the quadratic formula, x equals minus 2 plus or minus the square root of minus 8 over 2. If I simplify that by taking out a common factor of 2, I end up with minus 1 plus or minus the square root of minus 2. This is where, because we've got a negative under the square root sign, if I change that to the square root of 2 times I squared, since I squared is minus 1, then x equal minus 1 plus or minus the square root of 2i. And that's the solution to that equation. So if the coefficients of the quadratic equation are real, and in this case we've got a 1 out the front of the x squared, a 2 and a 3. So all the coefficients are real. Okay, and if we have a look at the roots that we get, they are the complex conjugates, because one of the roots is minus 1 plus root 2i, and the other root is minus 1 minus root 2i. And because they are exactly the same except for the sign in the middle, then they are complex conjugates. So if their quadratic has real coefficients and the roots are non-real, then the roots will be complex conjugates.